Welcome to this session. In this session, we will learn about compact set. In earlier lecture, we have seen that every closed subset of a compact set is compact. Every closed subset of a compact set is compact. Now, using this, so we know that a set is said to be compact if every open cover has finite subcover. So using this, the next important result is prove that the intersection of an arbitrary family of compact sets containing at least one point in common is compact. So let me write this statement. Prove that the intersection of an arbitrary family of compact sets containing at least one point in common is compact. So compact set. So for proof of this, we will use the previous result, this one. We already know that every closed subset of a compact set is compact. This proof we have seen. So suppose this A lambda, where lambda belongs to index set, be an arbitrary family of compact set. Be an arbitrary family of compact set. That is, each member of this family is a compact set. Then each A lambda will be closed and bounded from Heisenberg theorem, that because every compact set is closed and bounded. So I can say that each A lambda, this implies each of the A lambda from this family is closed and bounded, being compact, is closed and bounded for lambda belonging to indexing set. Now suppose, let us denote their intersection. By S, by this notation. Intersection of all those these compact set, let us denote it by S. Since the intersection of an arbitrary family of closed set is a closed set, actually each A lambda is closed, and we know that arbitrary intersection of closed set is a closed set. Let me write here arbitrary intersection of closed set is closed. So I can say this implies that this S is also closed, and being intersection, it will be subset of each of the A lambda. So also this set S is contained in each of the A lambda. Why? Because it is the intersection of all these compact set denoted by A lambda. So I can say that, so what we have here, that S is closed, and being subset of a bounded set, S is also bounded. S is bounded because S is bounded. So from this result that we know that every closed subset of a compact set is compact. Actually, each of the A lambda is compact and S is closed. So using this result that every closed subset of a compact set is compact, this implies that S is compact. Set S is compact. So this notation I have taken from the book of by N.P. Bali, Real Analysis by N.P. Bali. Now let me discuss some examples based on this. So in this continuation, there is a problem, example 3. In book by N.P. Bali. Let me explain this. Suppose the set is given by 1, 1.1, 0.9, 1.01, 0.99, 1.001, 0.999. Now question is, the first question is this set bounded? Is set S bounded? Second question, does the set S have least upper bound and greatest lower bound? If so, determine them. Does the set S have least upper bound and greatest lower bound? If so, determine them. Third question, does the set S attain its bound? Does the set S attain its bound? Fourth one is, find the interior of this set. Find the interior of set S. Fifth question, does the set S have any limit point? If so, determine them. Does this set have any limit point? If so, determine them. Sixth part, is S closed? Is this set closed? And the last part, is this set a compact set? Is this set a compact set? So we will discuss all these cases one by one. Now look at the set S here. Basically this set, we can write this set as this S is equal to 1, the first element is 1, and after this each element can be written as in this format, 1 plus minus 1 by 10 raised to the power n, where n belongs to n, where n belongs to set of natural number. 1.1 can be written as this as 11 by 10 or 1 plus 1 by 10. Similarly, this can be written as 1 minus 1 by 10. So in general, we can write this set as 1 union 1 plus minus 1 by 10 raised to the power n for n belonging to n, set of natural numbers. So clearly this set is contained into, we can contain this set into any bounded set. Say this set S is subset of, clearly its least element is 0.99 and the largest one is say 1.11, and every element is enclosed in between, or it have upper bound as well as lower bound. So clearly this set is bounded. So I can write here that this set is contained into 0.9 to 1.1, being contained into a set of finite diameter, or we can say that it has upper bound. Every real number greater than equal to 1.1 is its upper bound, and every real number less than equal to 0.9 is its lower bound. So this set is clearly bounded. So answer is yes, this set is bounded. Second is, does the set S have least upper bound and greatest lower bound? So for this, we know that whenever a set is bounded above, its supremum is this. Supremum is defined as among all upper bound, the least one is called as supremum. So actually here we need to find supremum of this set. So for supremum of this set, one can see that supremum of this set is among all real number greater than equal to 1. Actually, if for upper bound, if we try to find the upper bound of set S, let me write in this way, that set of upper bounds first. Set of upper bound is all real number x greater than equal to 1.1. These are the set of where x belongs to R. Set of upper bound. So among all these upper bound, the least one is 1.1. So I can say that its least upper bound is 1.1. Similarly, one can find this here set of lower bound. Set of lower bound of the set S is all those x which is less than equal to 0.99, 0.9, where x belongs to R. So among all these upper bound, the largest one is 0.9. So I can say that its least upper bound is, greatest lower bound is 0.9. Now question, third part is, does this set have, does the set S attain its bound? So yes, it attains its bound. Even in fact, every real number greater than equal to 1 is greater than equal to 1.1 is its bound, and every real number lower than less than equal to 0.9 is its lower bound. Now next part is find interior of the set. Find interior of the set. So recall, those points are said to be interior point of the set if around each point, if around those points we can construct at least one epsilon neighborhood which is sitting inside this set S. If you look at this set is countable. This set is countable because here n belongs to n. N is countable, so we have countable choices. In fact, countably infinite. So this set is countably infinite. Countably infinite. I have already discussed all these things in my previous lectures. So question is, does find the interior point of set S. Find the interior point of set S. So suppose there is some x belonging to set which is an interior point. So if this is an interior point, so around that we must have interval x minus epsilon, x plus epsilon, x plus epsilon. There exists some epsilon greater than 0, such that this interval is sitting inside the set S. But what is happening here? For epsilon greater than 0, we know that this interval is uncountable, and this set is countable. This set is countable, given set is countable. So an uncountable set cannot be contained into a countable set. So none of the members of the set S is going to be its interior point. So I can say that its interior point is 5. S naught denoted by interior of the set S is 5. Because we are not able to find any interval. If we construct such interval, then it will never be contained into this set S, because set S is countably infinite, and an uncountable set cannot be contained into countable set. So in simple language, we can say that none of its points are interior point, hence S naught is equal to 5. Now next question is, does the set S have any limit point? If so, determine them. So one can see that clearly its limit point are 1 and its limit point is 1, because from Archimedean property of R, in every neighborhood of 1, one can find, in every neighborhood of 1, it's 1 is its limit point. Let me write here, this set, 1 is its limit point. 1 is limit point of the set S. Why 1 is the limit point? Because for every epsilon greater than 0, 1 minus epsilon, 1 plus epsilon, every neighborhood of 1, will contain infinite members of the type 1 plus minus 1 by 10 raised to the power n from Archimedean property of real number that already have discussed. That there exists some m naught greater than some m naught belonging to n, such that for every n greater than equal to m naught, one can choose 1 by 10 raised to the power n in every neighborhood of, let me write it, for every epsilon greater than 0, whatever neighborhood we choose for 1, its intersection with the set is non-empty. Its intersection with the set other than 1 is non-empty. Now how to show this? So this can be claimed by from Archimedean property of real numbers. Archimedean property of real numbers, that this intersection is even except why? Because for every epsilon greater than 0, one can always have let me write here Archimedean property of real number, that for every epsilon greater than 0, there exists some m naught belonging to n such that 1 by 10 raised to the power n, 1 by 10 raised to the power n is less than epsilon for every n greater than equal to n. So from here I can also write that 1 plus minus 1 by 10 to the power n, 1 plus minus 1 by 10 to the power n is less than 1 plus epsilon. So in this interval, I mean around 1, if we have here 1 minus epsilon, here 1 plus epsilon. So in this we have the elements of the type, infinitely many elements of the type 1 plus 1 by 10 raised to the power n, and similarly here we have infinitely many elements of the type 1 minus 1 by 10 to the power n for every n greater than equal to that m naught. So one can always do this construction. So this is the reason why this intersection is non-empty. Why this intersection is non-empty? So one can claim from using Archimedean property of real numbers that this set has only one limit point 1. Similarly, other limit point cannot be discarded. So for this, how to discard other limit points, you can refer my earlier lectures in that I have discussed in detail. Let me explain one of the how to discard that only that 1 is the only limit point. So for that, what we will do, suppose let me take this 1.1 here. Is 1.1 is its limit point? So you can see that if on number line, let here denote 1.1, 1.01, all this, yes, 1.1, and left to it the numbers are 1.01, 1.01 and 1.1. Say yes, 1.1 is the largest one. So if we measure the distance of this 1.1 to the nearest one and take epsilon of this radius, then one can see that except 1.1, there is no member common from this element, common from this set with this neighborhood, So this is the reason that why no member other than, similarly, just here I have discarded that 1.1 is not its limit point. Similarly, one can discard that 0.9 is also not its limit point. Because if we measure the distance of 0.9 to its nearest element and then take the half of the distance around 0.9 and make an interval. So apart from 0.9, no element is going to be common with the set A. So in this way, one can discard that no other points are going to be its limit point. But around 1, from Archimedean property of R, this can be made less than epsilon, whatever epsilon one can choose. So I can say that in fact 1 plus minus 1 by 10 to the power 1 plus 1 by 10 to the power n type elements will lie in this neighborhood of 1 minus in the neighborhood 1 minus epsilon to 1 plus epsilon. So in this way, one can discard that 1 is the only limit point of this set. Now question is this set closed? So we know that for closed, a set is said to be closed if it contains all of its limit points. So clearly 1 is already there in the set. So we can say that. Answer is yes. This set is closed. Now is this set a compact set? Is this set a compact set? So from Hein-Borel theorem, we know that because here this set is closed as well as bounded, we have already proved that this set is bounded by enclosing it into an interval of finite length. We have already proved it bounded. Here we have proved that this set is closed. So from Archimedean property of real numbers, already I have discussed the proof of Archimedean property of real number, that so this set is going to be compact. Closed and bounded sets are compact in R or subset of R with respect to usual distance. So this set is going to be compact. Using Hein-Borel theorem, yes. So answer is yes. Using Hein-Borel theorem. So give a reference of Hein-Borel theorem. Next question. Which of the following sets are compact? Give reasons. So in this, the first one is closed interval 0, 1, whether this set is compact or not. Second, closed interval minus 1 to 1 union 2 to 3. Third one, set of natural number. Fourth, set of integers. Fifth, set of rationals. Sixth, open interval 0 and closed at 5. Seventh, closed at 2 and open at infinity. So we need to check whether these sets are compact or not, whether these given sets are compact or not. So clearly this set is closed and bounded. So from Hein-Borel theorem, this is going to be compact. Closed and bounded, hence compact. So answer is yes. What about this one? Again, this one is a compact set. This one is a compact set. This, in fact, this is the union of two closed set. Finite union of closed set is closed. So I can say that this set is closed, and closed as well as bounded because its diameter is finite. Or all real numbers greater than equal to 3 is its upper bound, and all real numbers less than equal to -1 is its lower bound. So clearly this set is bounded. Hence by Hein-Borel theorem, this is also compact. Now what about set of natural numbers? Say in set of natural numbers, we have already seen that there is no limit point for set of natural number. In fact, the derived set of a set of natural number is empty. There is no limit point, and phi is subset of every set, hence set is closed. Or in other words, we can say that there is no limit point which is not contained in the set. Actually, a set is said to be closed if it contains all of its limit point. So to discard that a set is not closed, just show that there exists at least one limit point which is not present in that set. So since here we have no limit point, so I can say that there is no limit point which is not in the set. So clearly this set is going to be closed. So set of natural number is going to be closed, but not bounded, Hence from Hein-Borel theorem, this set is not compact. So answer is no. Set of natural number is not compact. What about set of integers? Again, the same logic which we have used in case of set of natural number. The derived set of Z is phi empty. Z dash, the derived set is empty, and empty set is subset of every set. So this set is closed but not bounded. Closed but not bounded. Hence this set is not compact. What about set of rational numbers? Set of rational numbers. Set of rational number is not bounded, and also it is not closed, neither closed nor bounded. Why? So because derived set of Q, set of rational, its limit point is whole R. Every real number is limit point of set of rationals. So irrationals are also its limit point, which is not contained in the set, hence this set is not closed. Again, its diameter is not finite, that it has no upper bound as well as lower bound. So this set is not bounded, hence from Hein-Borel theorem, this set is not compact, What about this one? 0 to 5. 0 to 5. This set is not closed. Why? Because 0 is its limit point. which is not in this set, not closed. As not closed, why? Because 0 is also its limit point. In fact, its derived set, just recall from previous lectures, is whole closed interval 0 to 5. So 0 is not in 0 to 5, this set. Its limit point 0 is not present in this set. So there exists at least one limit point which is not in the set, hence this set is not closed. However, it is bounded because its diameter is finite. Every real number greater than equal to 5 is its upper bound, and all real numbers less than equal to 0 is its lower bound. So clearly this set is bounded but not closed, hence from Hein-Borel theorem, it is not compact. What about this one, 2 to infinity? This set is closed but not bounded. Closed but not bounded, hence not compact. So one can see that a set of natural numbers, set of integers are example of a closed set which is not compact, are closed but not compact, are closed set but not compact. नहीं है, बंद कर दिए, मैं क्लास ले रहा हूं, ठीक है. Okay. So since this neighborhood U from Archimedean property of real number, this neighborhood which is neighborhood of 0, is going to contain infinitely many members of the type 1 by n. Due to this, infinitely many members of the type 1 by n, only at most m naught members can be outside this neighborhood. So U is one of the set, and suppose the members now actually 0 belongs to U here, and the members left are 1 by 1, 1 by 2, 1 by 3, up to 1 by m naught minus 1, 1 by m naught 1, because starting from this m naught, every member is going to satisfy this condition. So how many members are left? This one. So what we can do, that for this 0 we have U. For this one, suppose there is, let us take any one open set from this. Suppose this one is U alpha which contains 0, or simply write it as U. And here let us take one open set which contains 1 from this family, or denoted by U1, U half, which consists of which contains half. Here U1 by 3, I can re-index it. U m naught minus 1, say U2, U3, U m naught minus 1. So how many total sets will be there? Whatever collection we have covering A, total number of set will be m naught. Here we have m naught, this one is m naught minus 1, and this one is one open set which containing infinitely many members. So total number of open set is again finite. That is, from Archimedean property of R, whatever set we choose containing 0, it will always contain infinite members of the type 1 by n, and outside it there lies only finite members, and those finite members can be covered by taking finite open sets from this collection, and thus we always have finite sub collection which is also covering this set A, I mean A can be contained to union of all these. So if someone want to claim it without using Hein-Borel theorem, then we have to do from Archimedean property, using Archimedean property of real number, we have to claim this. And from Archimedean property, and if someone want to use Hein-Borel theorem, then using Hein-Borel theorem, but we have to show that this set is closed and bounded. So clearly this set is bounded. Why? Because every member of the set A is contained in 0 to 1. I mean, each member set A is contained into 0 to 1. This one is a finite set. I mean, this one is a bounded set, and A is contained to bounded set. So this is also going to be bounded. So A is bounded, and the limit point of this set is 0, which is already there in this set. We have already seen in earlier lecture that the limit point of the set 1 by n is 0, which is already present here. So this set is closed also. So using Hein-Borel theorem, I can say that every closed and bounded set is compact. So this is by using result of Hein-Borel theorem. But if you want to prove without using Hein-Borel theorem, then you have to take help, because this only Archimedean property of real number guarantees you that every neighborhood of 0 will contain infinitely many members of the type 1 by n, and outside it there lies only finite members. And those finite members of the type 1 by n can be covered by using finite open set from this family, and thus in total we have always a finite subcollection.